Yes, good morning all of you. So in previous class we have seen what is matched filter, what is the uh, frequency response function of matched filter proposed by the north, and also its impulse response. Okay. Now in this class, let us see the derivation of matched filter characteristic, the derivation of the matched filter characteristic using Square's inequality theorem. Okay, derivation of the matched filter characteristic using Square's inequality theorem. Okay, so this is the topic now I would like to discuss. Okay. Okay. Now already we know the definition for the matched filter is. What is the definition for the matched filter? Which maximizes peak signal to mean noise ratio is referred as the matched filter, right? So let note down all of you once again. We know that is a frequency response function of the linear time invariant filter which maximizes the output peak signal to mean noise ratio for a fixed input signal to noise ratio is called the matched filter. Okay. So for this the response function proposed by the north is h of f equal to ga s star of f e power minus j 2 pi f t1. Okay, this is the response function of the matched filter proposed by the north. Okay, so up to this actually we have seen in the last class itself. Okay, now which you have to maximize is under the assumption of the stationary and white noise. Okay, under the assumption of the input noise type is stationary and white. So why this assumption we have taken? Because it has a uniform spectral density, that's why. Okay, therefore we have to maximize S naught of t mod S naught of t maximum square divided by n. Okay, S naught of t maximum square divided by n. So that is peak signal to output peak signal to mean noise. Output peak signal to mean noise. Okay, this we have to maximize. We have to maximize this one. Okay. Now in the numerator part is the output signal. Okay, maximum value of the output signal is the numerator part S naught of t represents, and the denominator n represents the mean noise power. Denominator n represents the mean noise power at the receiver output. Mean noise power at the receiver output, capital N means. Okay, whereas this is the now let us see the numerator part. First of all, I am going to derive the numerator part, after the denominator part, then combining this numerator and denominator, that is substituting in equation 1 and equation 2, equation 1, numerator and denominator, you can get the what is the ratio RF. Okay, now coming to numerator part. Okay, so numerator, for that I am going to consider one matched filter with the input is S of t and its impulse response is h of t. Therefore its output S naught of t we can express as the convolution of these two, the convolution of input S of t and impulse response h of t is the output. So that we can express it as S naught of t equal to S of t star h of t. Okay, S of t convolution with h of t like this. Okay, but in frequency domain it may be S of f into h of f, S of f into h of f. Therefore the output S naught of t you can express as integral of minus infinity to infinity S of f into h of f into e power j 2 pi f t dt, 2 pi f t dt. So the output we can express as like this, integral of minus infinity to infinity S of f h of f e power j 2 pi f t df. Okay, are you following up to this? Now this is the S naught of t value. Okay, but as per the numerator what it has, the magnitude of this value you can express, and square of this you have to consider. Okay, so therefore apply magnitude and square on both sides. The equation comes like, okay, with the applying of magnitude on both sides, it is mod of s naught of t equal to mod of integral of minus infinity to infinity s of f h of f e power j 2 pi f t df. Okay, so this is the equation when you apply the magnitude on both sides. Now squaring on both sides. Now squaring on both sides gives like this. Say assume this is equation 2. Actually this is the numerator part. This is the numerator part. Okay, this is the numerator part, and assuming it as equation 2. Okay, following. So this is the numerator part and assuming it as 2. Okay, now let us see the denominator. What is denominator? Denominator is capital N. It is mean noise power, right? Mean noise power, so that it can express as n naught divided by 2 integral of minus infinity to infinity mod of h of f whole square df. Okay, so the denominator represents the mean noise power. Mean noise power, it is expressed as n naught by 2 integral of minus infinity to infinity mod of h of f square df. Okay, this is a nice denominator part, and say equation 3, it is equation 3 already. Equation 2 represents the numerator and equation 3 represents the denominator. Now substitute equation 2 and 3 in equation 1. So substitution of equation 2 and 3 in equation 1, so that the RFF comes like this. Therefore RFF equal to write down the numerator, that is equation 2 is the numerator part and equation 3 is the denominator part. Okay, so with this substitution, now we are going to replace the numerator part by applying squares inequality. Okay, now the numerator part, whatever the numerator part here representing is again its representation is in the squares inequality. Okay, now what is squares inequality? That is, if p and q are two complex functions. Suppose if the p and q are two complex functions, then integral of p star p is p star p dx into integral of q star q dx is greater than or equal to mod of integral of p square q dx whole square. Following, this is the theorem of squares inequality, and the equality sign applies when p equal to kq, but where k is a constant. Okay, the equality sign is applies when p equal to kq and k is the constant. Okay, so this is the squares inequality theorem. Now as per this theorem, how the numerator part will be modified, that we can see now. Okay, yes, from this, in the right hand side, how the appearance is, it is in the magnitude form and also squaring form. Same our numerator also like this, and in the integral you have p star and q. Okay, now let p star is as per our equation in the numerator part. Let assume p star is s of f e power j 2 pi f t1. Let us assume p star equal to s of f e power j 2 pi f t1 and q equal to h of f. Okay, so assume in our equation, the right hand side part, the numerator, p star is this part and q is this part. Okay, again by recalling the statement like integral of p star p equal to dx equal to integral of p square dx, so that the numerator is expressed now separately h of square and s of square. The denominator part as it is, you write only denominator part is as it is. Okay, by observing this, what will happen? H of square in the numerator, h of square in the denominator will be cancelled. These two get cancelled. Therefore, the rest is r of f equal to integral of minus infinity to infinity s of f square df divided by n naught by 2. Okay, so this is the equation now we got, And again here by applying the Parseval's theorem. Okay, by applying the Parseval's theorem. So what is the Parseval's theorem represents? So integral of minus infinity to infinity s of f square df, or in the time domain also represents the signal energy that equal to capital E. So that the RF is 2 times of capital E divided by N naught. Now how much we got? 2 times of signal energy divided by the N naught. Okay, RF is less than or equal to this much. But equality sign is applied when P equal to KQ, right? E equal to KQ. Now already we know that P star equal to S of f e power j2 by ft1, and we assumed that Q equal to hf. Okay. Since suppose if P star equal to S of f is S of f e power j2 by ft1, what is P? P is, you can express S star of f e power minus j2 by ft1. So like that you can interchange. Okay. Now this is the P. Now this is the P and Q is h of f. Okay. Then substitute these two in P equal to KQ, E equal to KQ. And that is, since P equal to KQ, substitute, it comes like h of f. Q means h of f equal to uh, 1 by k into s star of f e power minus j 2 by f t1. Okay. Now that 1 by k is replaced by ga. Okay. Therefore, the equation which is proposed by North we get. Okay. So and this is the derivation for the match filter characteristic using Schwarz inequality theorem. Okay. Okay. Thank you.